You know that golden telescope we humans built that's taking some mind-blowing pictures of space right now? Well, it turns out it's so powerful it might have just shattered our understanding of the universe.
A revolution in our understanding of the universe is coming. And the source of transformational insights is the James Webb Space Telescope's groundbreaking observations themselves. The whole world was gobsmacked when the James Webb Space Telescope, or JWST, released its first clutch of images, showing us the universe like never before. It was the $10 billion US gift to the world. And now the telescope continues to stun us when it captures the farthest individual star known in the universe, revealing the discovery challenges our theories of stellar evolution itself. Join us today as we uncover James Webb's new discovery of the most distant star ever and delve into how James Webb upended our understanding of the cosmos. Without any delay, let's get started. James Webb Space Telescope launches astronomy into a new era. Indeed, the history of science could be written as a history of instrumentation, from particle accelerators and microscopes to functional magnetic resonance imagings, or fMRIs, and telescopes. As instruments become more powerful, they act as reality amplifiers. They magnify our view of the very small and the very large, allowing us to glimpse what is invisible to the human eye. It is hard to imagine that, up until 1609, all we knew about the skies depended on what we could see with the naked eye. When Galileo Galilei had the insight to aim his telescope at the night sky, he saw what no human had ever seen before: a new sky full of surprises and possibilities. This new sky would reveal a new world order. Out with an Aristotelian view of an Earth-centered cosmos, a frozen sky where celestial objects were perfect and unchangeable, and in with a marvelously imperfect heaven, a moon full of craters and mountains, Jupiter with 4 orbiting moons, now we know there are about 79 and counting though, a Saturn with ears, that is, the rings that his telescope could not yet resolve, and a Milky Way made of a countless number of stars. New instruments hold the promise of a worldview transformation. As we look deep into nature, our vision of reality and us in it changes. It is then no surprise that the astrophysics community was so excited while witnessing the launch of a new marvel of instrumentation, the James Webb Space Telescope, JWST. Even if it is often called the successor of the Hubble Space Telescope, or HST, the JWST is a different kind of machine altogether, and it surpasses the Hubble in several ways. James Webb will allow astronomers to look not only farther out in space, but also further back in time. It will search for the first stars and galaxies of the universe. It will allow scientists to make careful studies of numerous exoplanets, planets that orbit stars other than our Sun, and even embark on a search for signs of life there. In other words, the Webb is a machine for answering unanswered questions about the universe, for exploring what has been unexplorable until now. As Amber Strawn, an astrophysicist at NASA who works on the Webb, said, "What we're going to get is a telescope that's about 100 times more powerful than Hubble." But how? The Webb improves on Hubble in 2 key ways. The first is just its size. Hubble was about the size of a school bus, where Webb is like the size of a tennis court. This thing is enormous, Strawn says. Webb is by far the biggest telescope NASA's ever attempted to send into space. But it's not just the total size of the contraption that matters. When it comes to reflecting telescopes, the key component is the size of its curved mirror. You could sort of think of a telescope mirror like a light bucket. The more light you can collect in this bucket, the fainter and farther away things you can see in the universe. Hubble's mirror was an impressive 7.8 feet in diameter. Webb's beautiful gold-hued mirrors combine for a diameter of 21.3 feet. Overall, that amounts to more than 6 times the light collecting area. And what does that mean in practice? Well, the short answer is, we're seeing farther back in time with Webb. With Webb, astronomers will be able to see so far back that they'll potentially spot the very first stars and galaxies ever formed. Hubble has seen light dating back to about 400 million years after the Big Bang, which took about 13.3 billion years to reach us. But Webb has the capability to take us to 250 million years after the Big Bang. That might not sound like a big difference. What's a few 100 million years between friends? Actually, it's the difference between seeing the first stars that ever turned on and arriving a bit too late after the funeral. Astronomers call this period, when the first starlight shone through the universe, cosmic dawn. With the Webb, humanity will be able to glimpse at it for the very first time. On the other hand, unlike Hubble, James Webb is primarily an infrared telescope, so it sees light that's in a longer wavelength than what our eyes can see. This seems nerdy and technical, but it's actually what allows Webb to look further back in time than the Hubble, opening new windows to the early universe. According to Sarah Sager, a planetary scientist and astrophysicist at MIT, the Webb represents the culmination of decades, if not centuries, of astronomy. We've been waiting for this for a very long time. With such great power, James Webb promises to transform our understanding of the universe. And the reality proved that the $10 billion US gamble is living up to its bill. The whole world was stunned by Webb's awe-inspiring images and confounding scientific discoveries since it began its epic science mission. Within just a few weeks of working, the Infrared Observatory has already discovered several candidate galaxies that quite simply challenge the Big Bang Theory and our galactic evolutionary models. And now, Webb has focused its instruments on the most distant star ever observed that began shining just 900 million years after the Big Bang. The images improve on those taken earlier this year by the Hubble Space Telescope, which discovered this ancient object and provided astronomers with their first glimpse of a star from the early period of the universe. Astronomers call this ancient star Earendel, a word derived from Old English meaning morning star or rising light. It began burning some 13 billion years ago, but because of the expansion of the universe, now sits about 28 billion light years from Earth, making it the most distant star ever observed. Astronomers know it's very old because its light is very, very red. Very old light is red because it's been stretched over time as it travels through space. Extremely distant stars and galaxies appear to move away from us at greater speeds than closer galaxies, so their light is redder. So the redder a star or galaxy, the earlier in the universe it existed. Earendel's light has a redshift of 6.2, while most stars found using gravitational lensing have redshifts of between 1 and 1.5. Notably, Earendel is only observable because of an extraordinary cosmic coincidence. As seen from Earth, it sits behind a vast cluster of galaxies called WHL 0137-08, with a gravitational field that focuses its starlight towards Earth, magnifying it up to 40,000 times. This gravitational lensing effect makes Earendel's host galaxy appear as a smear of light across the distant universe. Astronomers have named it the Sunrise Arc. The arc contains bright knots of light along its length, and one of those knots is Earendel. JWST's images improve on Hubble's and narrow down the potential size of this star. The star appears as a point star of light, suggesting it cannot be greater than 4,000 astronomical units across. These new observations strengthen the conclusion that Earendel is best explained by an individual star or multiple star system, says Brian Welch at Johns Hopkins University in Baltimore and colleagues who have analyzed the images. The team there says that the photometry suggests Earendel has a surface temperature of between 13,000 and 16,000 Kelvin. This in turn suggests the star is a giant hydrogen-burning B-type star with a mass somewhere between 20 and 200 times that of our Sun. However, the team also say that Earendel could be a binary system and that various combinations of stars could better fit the observed data. Indeed, the best fit is a combination of a luminous cool star and a hot companion. For the moment, the data does not allow the team to solve this problem. However, JWST is due to observe Earendel again later this year, when more data could help to constrain the nature of this star or the star system. It will also provide astronomers with more data about one of the universe's very earliest stars. That's interesting work that allows off the extraordinary light-gathering power of the JWST and its older relative Hubble. And now this instrument is already changing the way we see the universe. Interestingly, not only capture the farthest star ever, but the James Webb telescope also detected the most distant active supermassive black hole to date. The galaxy that holds the ancient black hole, Sears 1019, formed fairly early in the universe's history, just 570 million years after the Big Bang. The active supermassive black hole at the center of Sears 1019 is unusual, not only for its age and distance, but also in that it weighs in at just 9 million solar masses, meaning it's 9 million times heftier than the Sun. Typically, most supermassive black holes in the early universe weigh in at over 1 billion solar masses, making them brighter and easier to detect. The relatively small size of the black hole at the center of Sears 1019 is somewhat of a puzzle. According to a statement from the Space Telescope Science Institute in Baltimore, which manages JWST's science operations, it is still difficult to explain how it formed so soon after the early universe began. Astronomers have long suspected that smaller black holes must have formed in the early days of the universe, but these observations are the first to see them in such detail. Researchers have long known that there must be lower mass black holes in the early universe. Webb is the first observatory that can capture them so clearly, said Dale Kosevsky of Colby College in Waterville, Maine, who led one of 3 new studies that used JWST to peer at the distant universe. Now we think that lower mass black holes might be all over the place, just waiting to be discovered, he said. The black hole in Sears 1019 was discovered using data collected by the JWST as part of the Cosmic Evolution Early Release Science Program, or SEERS survey, a research program designed to test and validate models to peer far back into the universe's history in a region of space between the constellations of Ursa Major and Boötes. The data collected for the survey already has astronomers simply thrilled. Until now, research about objects in the early universe was largely theoretical, said Steve Finkelstein, an astronomer at the University of Texas at Austin, who leads the SEERS survey and co-authored one of the studies of Sears 1019 that used JWST's data. With Webb, not only can we see black holes and galaxies at extreme distances, we can now start to accurately measure them. That's the tremendous power of this telescope, said Stephen Finkelstein. JWST was able to collect a wealth of spectral data on Sears 1019, the electromagnetic signatures that reveal the chemical composition, mass, and older properties of the galaxy, the data reveal that the galaxy is actively producing new stars, possibly as a result of a merger with another galaxy that is feeding the activity in Sears 1019's central black hole. In addition to detecting the black hole at the center of Sears 1019, the survey also found two other lightweights, supermassive black holes with smaller masses than what is typically seen in black holes at that distance. These two black holes at the cores of the galaxies Sears 2782 and Sears 746 formed 1.1 billion years and 1 billion years after the Big Bang respectively. Each weighs in at around 10 million solar masses. For comparison, the black hole at the heart of our Milky Way galaxy, known as Sagittarius A, is about 4.3 million times more massive than the Sun. But that's quite the light for a modern supermassive black hole. The behemoth at the center of galaxy M87, for example, harbors about 6.5 billion solar masses. 11 galaxies in total have been discovered using JWST's Sears survey data, galaxies that are thought to have formed between 470 to 675 million years after the Big Bang. The data produced by the study of these galaxies could revolutionize astronomers' understanding of how stars and galaxies formed and evolved throughout cosmic history, researchers say. I am overwhelmed by the amount of highly detailed spectra of remote galaxies Webb returned, said Pablo Aralbo Hera of NORI Lab, a lead author of one of the studies using Sears survey. These data are absolutely incredible, he said. Extending the winning streak, James Webb most recently revealed yet another masterpiece. This time around, the machine has presented us with a mesmerizing scene of two actively forming young stars tucked into a pocket of space about 1,470 light-years away. Produced with the scope's powerful infrared eyes, the image showcases a striking salmon-colored smear at its center. This represents the area where the stars, collectively named Herbig-Haro 4647, are found. To be clear, because scientists captured everything you see here by harnessing the James Webb Space Telescope's infrared sensors, this image would have originally been in black and white. Those fiery oranges, pale blues, and textured pinks you see were added later to enhance the frame and make it easier to glean scientific information from it. For instance, you'll see two conical regions of darkness on the glowing splotch's left and right side. Imagine how the figure is actually in 3D. These structures represent shadows of a gassy, dusty disk floating within the rose-colored blob. This disk tightly surrounds the stellar duo, feeding the baby stars as they grow and mature, a process expected to culminate millions of years from the point the JWST has isolated. Beyond those structures, NASA calls attention to the main event of the JWST's latest muse, two huge lobes peeking out on either side of the disk. The smaller right lobe falls closer to Earth, while the larger left one sits further away. These lobes are made up of stuff from the dusty disk the stars once ingested, then later spit out into the void of space. Such ejections are considered very important in the act of star formation. You can think of them like a fountain, the agency explains, rapidly switching on and off to form patterns in the pool of our universe. Once these young orbs finish their growth period, they'll ultimately clear the scene of its chaos. In the background, it's impossible not to notice the dense symphony of stars and galaxies scattered across our universe. Some are old, some are new, some are big and others are small, but each one is equally profound in the realm we call home. Almost like an artist's signature, the JWST left its classic 8-pronged diffraction spikes all throughout the image. 2 of the spikes are tinier than the other 6, running horizontally through the center. Photos produced by the Hubble Space Telescope, for instance, exhibited 4 spiked stars. It really depends on how many mirrors a machine has, which is why they're called diffraction spikes. But when you see those 8, you'll know it's a JWST image. Using these features as a guide, there are a few intriguing goodies to zoom in on. If you lower your eyes to the center red diffraction spikes, you'll catch Herbig-Haro 4647's most recent ejections. These are shown as strings of blue that move outward until they turn into a light purple halo. Around this diffraction structure are curly, pale blue lines which NASA says are also associated with the star's ejection patterns. Don't worry, both are relatively difficult to see as they're so close to the JWST's spiky penmanship. Though what you most definitely cannot miss is the ethereal azure curtain surrounding the angry red blob in the middle. This is another cosmic object known as a nebula, a massive cloud of dust and gas. The JWST is specifically built to filter past such hazes and allow us to peek into whatever lies within, in this case, Herbig-Haro 4647. In fact, because of JWST's capability, this image marks the most detailed portrait of these stars to date. Thanks to the telescope's high-resolution near-infrared imager and the various exposures it's programmed to tap into, scientists broke past the nebular veil. Further, the nebula is also why the star's jet appears to be lit up, according to a press release put out by the JWST team. As ejected materials ram into the nebula in the lower left, the researchers explain, it takes on wider shapes because there's more opportunity for the jets to interact with molecules within the nebula. And thus, the sparkling spectacle we've now been blessed with, a picture literally worth 1,000 words. It's so rich with information that even the wealth of image data discussed throughout this video doesn't quite cover the half of what astronomers will be able to learn from it in terms of how stars form. Well, that's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode. Subscribe if you haven't already and share with your friends. And hit the bell so you never miss out on future episodes. And be sure to tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we'll see you next time.